So today I want to talk a little bit about the Stern-Gerlach experiment, okay, the SG experiment. And I have a few concerns about this experiment, not in the experiment itself, but in the interpretation of this experiment. Okay, so I asked ChatGPT to give me a short, one or two sentence synopsis of this experiment. And so this is what I got. Okay, so the Stern-Gerlach experiment demonstrates the quantization of angular momentum by passing a beam of silver atoms through a non-uniform magnetic field. The magnetic field splits the beam into discrete paths, revealing that the atoms' magnetic moments align with only specific orientations, providing direct evidence of quantum mechanics. Okay, so I simplified this. The only thing we really know for sure about this experiment is that the Stern-Gerlach experiment passes a beam of silver atoms through a non-uniform magnetic field. The magnetic field appears to split the beam into two distinct paths. Okay, so those are the only two honest sentences in this synopsis here. I think that it makes more sense to start with this and not make any assumptions about what this means. Okay, so I want to take a few steps back and maybe rethink this experiment a little bit and see if maybe this splitting of paths might have an alternate interpretation, an alternate meaning. So in this experimental setup, we do in fact have a source of silver atoms that are being transmitted through this tiny slit. This gets heated up and the silver atoms have kinetic energy and they go through this slit, and they do in fact go through these two magnets. Now these two magnets have a strange configuration where they have different shapes, and this supposedly creates different magnetic field strengths. Okay, and then the silver atoms pass through here and they go up and they go down. Okay, so they don't go here. So what their expectation was, based on their current theory at the time, was they would see a spread of electrons appearing in this region here that is painted white. But in fact what they saw were just two split signals where there were electrons found, or atoms detected up here and atoms detected down here, and very little, if any, atoms in the middle. So the probability of finding an atom hitting this part of the detector was very low, and the probability got higher as you got into these other regions. And so it is my feeling that there might be another interpretation, another explanation for this, and so that is what I want to address in this video. So as you may well know, if you've been following my channel closely, that I'm actually a big fan of this field diagram here, which are the isopotential, the equal potential field diagram of a magnetic configuration. So what I did was I used Michael Snyder's Pictomag software to generate these images here, and so I used it to, generated something that looked kind of similar to this diagram here, okay, with a triangle-ish shape and this kind of shape here, just to see what the isopotentials would look like. And so this over the left here, what we have are the standard magnetic field. This is the orientation of magnetic moments in different locations surrounding this magnetic configuration. And here we have what the isopotentials would look like if we could actually make this kind of configuration. So the one thing that bothers me about this experiment, obviously here it looks like I've got magnetic monopoles. So you've got these poles kind of hanging in the middle of nowhere, and that's what they do whenever they depict the Stern-Gerlach experiment. They show that the one above is always the North Pole and the one below is always the South Pole. and it gives kind of the false impression that you could have magnetic monopoles, which we know aren't true. But let's just pretend for this thought experiment that you can have. Obviously, there's going to be a south pole up here and a north pole down here, but I'm mostly concerned about what's going on in between these two magnets. Okay, in between these two magnets. And so here what you can see is when you look at just the magnetic fields, okay, when you look at just the magnetic fields, it's very difficult to see the isopotentials. Okay, the isopotentials don't jump out at you when you look at this field diagram here. But when you look at this field diagram here, you can see that I'm going to zoom in on it a bit, you can see that the dipole moments are always orthogonal to the isopotential lines. So I can actually look at the isopotential diagram and I know exactly what direction the magnetic moments are going to be oriented, because they are always going to be exactly orthogonal to these lines. And of course, there aren't any lines, there aren't any curves, there are an infinite number of potential magnetic moments in this region here. And so what we are showing here are just the lines of equal potential. So you may remember that at one point I did an experiment where I used a Hall sensor and a device that I got from a friend of mine who sent this to me, where I could convert that into a voltage. And so I was physically mapping out these isopotentials using this device here. And what I found was, so this is obviously a gradient. This is forming a gradient. So let's say if this was 1 volt, then this would be 2 volts, and this would be 3 volts, and this would be 4 volts. And this is how this gradient is formed. And you can think of this as, since it's a voltage gradient, you can interpret it as a pressure gradient. And for sure, when you put two magnets together in repulsion, it really does feel like there's a pressure there. So this is you can think of this as a pressure gradient. You can think of it as a voltage gradient when you're using a Hall sensor to measure it. And so I think it is reasonable to think of this as a pressure gradient. And so when you look at the magnetic fields, when you look at the, as if they are iron filings surrounding the magnetic configuration, you don't really get the real feel that there is a pressure gradient going on here. Okay, so that's the first point I want to make about how maybe possibly we can reinterpret the Stern-Gerlach experiment. Okay, I think we need to be looking at what this guy is doing and not the magnetic fields necessarily. Okay, the standard magnetic fields that they normally show when they are depicting this experiment. Okay, so this is just one piece of the puzzle. There are actually many pieces of the puzzle. There are many things that sort of come into my thinking about the Stern-Gerlach experiment, and they're all interconnected and related. So it's not just about one thing, but this is just one piece of the puzzle. Now, the next piece of the puzzle I want to show you has to do with this here. So what I'm going to do is I'm going to play you a video I made where I take some small magnets and place them on a big spherical magnet and show you the behavior of these magnets in this scenario, because I want to be talking about the behavior of small magnets in the vicinity of large magnets. Okay, and so in the Stern-Gerlach experiment, you have small dipole moments. I'm not going to call them magnets anymore. I'm just going to call them dipole moments. So you've got a tiny, tiny, tiny atomic size dipole moments in the vicinity of an extremely large, by comparison, dipole moment. Okay, this is a magnet, it's a dipole moment. And so you are passing these, I want you to keep in mind that we are passing these silver atoms between these two magnets, okay? And so here you'll see, when I show you the video, you'll see that I marked out the middle point of the magnet, which Kent Wheeler refers to as the dielectric inertial plane. And so this is a special region in the magnet, because this is the region that's exactly halfway between the North Pole and the South Pole. Okay, so I'm going to play this video I just have to get set up so that you can hear actually what's going on, and then we'll play this video. So I want to show you something here with the sphere magnet. Okay, so here we have a fairly large neodymium sphere magnet, and what I have are a couple of small magnets here and here. I have sort of a, like, not a bar magnet, but a cylinder magnet that's kind of longer. It's not round, it's not spherical. And then I have a couple of really small spherical magnets that want to sit here. Okay, so what I want to show you is, so the North Pole is facing this way. So I painted the top of the cylinder magnet red. Okay, and what I want to show you is I'm going to place, so here I've drawn a line. Okay, I've drawn a black line along the center of the, what Ken Wheeler calls the dielectric inertial plane. Okay, and you'll see that the cylinder magnet sits quite nicely on this line here, and when I try to turn it, it doesn't want to turn. So it's almost impossible for me to, on purpose, turn this cylinder magnet so that it sits on this line. So it is almost impossible for me to anti-align this cylinder magnet with the big magnet. Okay, and hopefully I don't want to get too close to my camera here because I'm afraid I'm going to wreck it, but so I'm going to place a sphere magnet as well. You can see I can easily place a sphere magnet onto the line. My lighting is also not that great, so I apologize for that. I just want to make this point because this is kind of the starting point for me when talking about the Stern-Gerlach experiment. Okay, Gerlach, or however you say that. I don't know how to say it. Okay, so here, what I'm going to do is, so also I cannot anti-align as soon as I get close to the magnet. So I'm turning the sphere magnet here, and as soon as I get close to the magnet, it turns to align with this magnet. Now it is anti-aligning in that the the South Pole here is pointing to the North Pole here, and the North Pole here is pointing to the South Pole here. And that is called aligning, because it's aligning in such a way. So if I let this go up here, you will see, maybe you can see the red, I'm not sure, but the North Pole is pointing this way and the South Pole is pointing this way. And when I slowly, let me get these out of the way, when I slowly drag this to the line, okay, the red points down and the not red points this way. So this is, I don't know whether this is aligned or anti-aligned, but it is aligned with the magnetic fields in standard, what would be called standard thinking. Okay, so what I want to show you here is, okay, where did my guy go? Okay, they attach to each other. Let me just put this back here. I got to keep them kind of far apart. Okay, so what I want to show you here, that it is easy to place the sphere magnet on this line, but all I need to do is touch it just a tiny bit. I need to bring it above this line, the dielectric inertial plane, the center line of the magnet, and it flies up. And in a similar manner, here it is sitting nicely, and when I push it just a little bit below the line, it goes to the South Pole. Okay, so it doesn't take much. So if it's just a tiny, sometimes I have a hard time getting it on the line. So if I just touch it a tiny bit, it flies to the North Pole. And if I just touch it a tiny bit this way, it goes to the South Pole. Now with the cylinder magnet, which is longer and not spherical, I can actually move it around quite a bit above the line, okay, before it flies to the pole. Okay, and same with the other pole, but I just want to show you that the longer, skinnier magnet behaves a little differently than the spherical magnet, in that it is the stability of it sitting on this plane is much longer. So I can move it all the way to here, all the way to here, then boom, then it flies to the top. So it's got maybe more surface area that's attracting to the magnet, and the spherical magnet has very little surface area touching the magnet, and so it's not as bound to the magnet, I guess you could say, as this one, but this one easily flies to the top and easily flies to the bottom. So in the discussion of the Stern-Gerlach experiment, we're going to be discussing these two scenarios, because in nature, the electrons are probably not a bar magnet. They're probably not a long, skinny cylinder magnet. They're more likely to be a like a spherical-ish shape. And so, and also, yeah. So that's all I'm going to say about that. I just wanted to show you this experiment here and how you can. And I do want to emphasize the fact that both the spherical magnet and the cylinder magnet do not nicely anti-align. I cannot anti-align it. I cannot spin this and get it to sit on the line. It's going to spin back to the original orientation. And this is also an important, I'm going to call it the SG experiment, okay, because I have a hard time saying that second name. So the SG experiment, in the SG experiment, they are saying that the electrons are either aligned or anti-aligned, but I don't believe they're ever anti-aligned. I will not believe that they anti-align with a magnet. So this is all about small magnets in the vicinity of a large magnet. Okay, so magnetism, magnets, dipole moments have the property of self-similarity, and this is what we're talking about here. So this small magnet is self-similar to the big magnet, and this is a small magnet in the vicinity of a very large magnet. And when that happens, you get, different kinds of behaviors depending on the shape of the magnet. Okay? Okay, so the main takeaway from that video that I want you to get is that if we have a small dipole moment going between two magnets, okay, let's say they're going between the two magnets through the dielectric inertial plane, if the atom is even a little bit above the central plane of the magnetic configuration, it's going to tend to want to go up. It's going to want to follow this isopotential line, let's say. If it's on this line when it comes out, it's probably going to follow that line because it's got velocity, okay? And so, and if it's just a little bit below, it's going to tend to want to go down. Okay, so, and if it's right in the middle, I think it's going to get caught up in one of these lines, and it's going to tend to want to go up, and it's going to tend to want to go down. So that is what I'm putting out there. I'm speculating that this might be another reason why they go up and they go down, but they don't go straight through, because they get caught up in this region here. They align with this magnet. They get caught up into one of these orbits, if you want to call it that. And so I'm going to talk a little bit about orbits. Okay, so I know that historically we had this term orbital, and that is what we're going to talk about next. So in physics, you'll run into this term electron orbitals, and so I asked ChatGPT to write me a couple of sentences on electron orbitals. And so electron orbitals are regions around an atomic nucleus where electrons are most likely to be found. Rather than following fixed paths, electrons exist in a cloud of probabilities, with each orbital having a unique shape, like spheres, dumbbells, or more complex forms, depending on the energy of the quantum state of the electron. These orbitals are described by quantum numbers, which arise from solving Schrodinger's equation for the atom, giving us a deeper understanding of the atomic structure. Okay, so why use the word orbital if it's a probability distribution, if it's not orbiting? Okay, So the term orbital originates from early atomic theory, which was heavily influenced by the idea of electrons moving in defined planet-like orbits around the nucleus, much like planets orbiting the sun. As quantum mechanics developed, this classical view was replaced by a probability one, where electrons were no longer seen as traveling along fixed paths, but instead existing in regions of space where they are most likely to be found. Okay, so so the next piece of the puzzle I want to show you has to do with this diagram here. Okay, so this diagram here shows a few examples of the electron orbitals. Okay, and we're going to primarily be focusing on this one here because this is a dipole moment. This is a dipole. It's got one positive and one negative. And what I want to show you is how similar these shapes are to the isopotentials of a magnetic moment, of a magnet. Okay, which is, what I'm showing you here. Okay. So what I'm also showing you here in the bottom are the resonances of acoustic resonators. So I showed you this in a previous video. These are sound fields radiated by simple sources, which are spherical resonators. Okay, so they radiate from monopole sources, and they're either in phase and they're out of phase, and the patterns they produce are identical to the electron orbitals and the isopotential diagrams from Michael Schneider's pick to mag software. Okay, and so I find this really, really interesting. Okay, I find these connections very, very interesting. And so what we have here, what I'm showing here, is the dipole orbitals, electron orbitals, and here is a very simple isopotential drawing for a simple magnet. And what I'm going to do is overlay these two and show you how the shapes are identical. So there is a distinct relationship. I call these self-similar patterns because there is a similarity to the patterns and there is a similarity to the scenario that's going on here. So here we have a positive and a negative charge, let's say, and here we have a north and a south pole, and yet the equations that are used to generate these two images also produce the exact same pattern. Okay, so I think this is a really important piece of the puzzle. And so what I want you to imagine, okay, now we're going to do a thought experiment because I can't actually do this experiment. So what I'm going to do is I'm going to put the electron orbital image here, and I'm going to imagine, so this is an electron cloud. This is the probability distribution of where the electrons are most likely to be found. And what I'm going to do is I'm going to put a wall here, a detector. So this is an electron detector device. This is a wall that is intersecting the electron orbitals diagram of the probability distribution of the electrons in this particular atom, in this particular configuration. And so you can see that if the wall intersects at this point, so this is an electron detector, so it's going to have a high probability of detecting electrons here. It's going to have a low probability of detecting electrons here, and then it's going to have a high probability of detecting electrons here. And so if we could look at the wall face on, we're going to see a dot here, and we're going to see a dot here, we're going to see electrons here, and we're going to see electrons here, and we're not going to see electrons here. Okay? So now what I'm going to do is I'm going to replace this diagram with this diagram. So this is the isopotentials of a magnetic dipole configuration with a north pole and a south pole. And now this isopotential diagram, this isopotential field of this particular magnet is intersecting the same wall. Okay, so what I want you to imagine, because we can't do this experiment, is that well, we can do this experiment in the Stern-Gerlach experiment, when we send electrons, when we send silver atoms with an extra electron in its outer shell through the dielectric inertial plane of a magnetic configuration. Obviously, we can't do it with this, but if we had a hole in this magnet, we would be able to send the electrons through. And what I was saying before is that the electrons maybe would go up this way or go down. If they're a little bit below the inertial plane, they're going to go this way. And if they're a little bit above the inertial plane, they're going to go this way. But if you also think of, because we are talking about electrons here, and we're talking about the property of self-similarity. So in the fractal model of the universe, I'm proposing that the magnet is no different than an atom, etc. And so these things can happen on different scales. Okay, here we have the electron orbitals, which are happening at the atomic scale, and here we have the isopotential, which is happening at the human scale. This is a magnet that I actually, of a size that I can actually hold in my hand. Okay, so I want you to imagine that instead of just thinking of it as the electrons passing through here and going up and down, which they do, you can also think of it as this is the probability of detecting an electron here is much higher than the probability of detecting an electron here, exactly analogous to the electron orbitals of an atom. And so it's possible that this is closer to the truth of why we don't find any electrons in this middle part, because the probability of finding an electron in this giant atomic structure, in this giant magnet, is much lower here than it is here, and that's why we see these two, we see some up here and we some up here, and we don't find any in the middle. Okay, so this is basically what I'm thinking. This is my line of thinking. It's interesting to see that when you apply quantum mechanics, which is the electron orbital idea, to the human scale, which is this magnet here, you see similar results. This is self-similarity, and so it may or may not have anything. So in the experiment that I showed you with the spherical magnet, there were no up magnets and down magnets. Okay, the magnets were always pointing to, correctly in terms of, so they were always aligning when they went between the magnets. So let me go back to that configuration. Okay, so when you pass a magnet, and I did this experiment myself, when you pass a magnet through two magnets that are separated by distance, they always align. Okay, let me just show you that. So here I have a graphic that I drew. Here is the magnetic configuration, and I'm imagining now these. I am imagining these as long skinny magnets instead of sphere magnets, but they're probably more likely like the sphere magnets in the experiment I showed you, where the magnets would easily fly up towards the North Pole or fly down towards the South Pole, depending on what side of the dielectric inertial plane of this central plane of the magnet they were on. And so you can imagine these magnets going through this magnet configuration, and if it gets caught up in this line here, it's going to go up, and if it gets caught up in this line here, it's going to go down. This is what the mainstream legacy physics calls an up electron, and this is a down electron, but there are no up and down electrons. They will always align. If you left to their own devices, throwing a magnet between two, a North Pole and a South Pole, they're always going to align with this field. There's no way that a dipole is going to anti-align while going between these two magnets, okay? So they might look like they're anti-aligned because when they go up, the North Pole hits the wall, and when they go down, the South Pole hits the wall, because they are always going to align orthogonal to these isopotential lines, okay? And so I think this is it's a misunderstanding. And I think I have one more thing I want to show you to verify that it is possible for small magnets in the vicinity of large magnet to follow the isopotential lines. And so there's another experiment I did in the past that I think will that demonstrates this very nicely. Okay, so here is a video I did where I show, so first I'm showing without any magnets what happens to the small magnet when just by the the magnetic field of the Earth. Okay, when there's no magnet, then the small magnet pretty much does nothing. Okay, so next I'm going to show, so once I'm done waving my little cursor there, let me just move this over a bit. So now what I'm going to do is I'm going to drop a magnet. Now the magnet is in place up here, and you can see that it follows a strange path. It actually goes backwards. Okay, so I have leveled everything in this experiment. Okay, so it is not, gravity isn't doing any of this. Okay, what happens is when I drop the magnet, it's got a tiny bit of kinetic energy. Actually here, I'm gonna let this play a little further there. So I think it makes more sense when I show the isopotential line. So you can see that the magnet, it goes backwards and it follows the isopotential line. So I drop the magnet, hardly even do anything to it, and then it follows the isopotential lines all the way back to the magnet. So it is basically orbiting. These are literally orbits. They're not like gravitational orbits, but they are literally orbits. The small magnet in the vicinity of large magnet wants to follow these isopotential lines. And this is because, for two reasons, I think. There's gravity, which is forcing the magnet down a little bit, and there's the friction of the paper. And so I think if the magnet was floating, I'm going to stop this. If the magnet was floating in free space here, it would fall directly into the magnet. If it's just sitting there, it will fall directly into the magnet. Okay, but because it's bound, a little bit bound to the paper, because gravity is pushing it down, it's a little bit bound. So in a bound circumstance, okay, the magnet is going to follow that isopotential line. So let's see what else I have here. More hand waving. Let me see. Okay, so I do it again. So now I'm doing two. So I've got a couple of magnets, and it gives it a little more stability. It's kind of like a wheel. You can see that it is reorienting itself all the way along the isopotential line. So no matter where it is, it's always oriented in the direction of the magnetic field. Okay, the correct direction for the magnetic field, but it is always following the isopotential. So, okay, so this is an important piece of the puzzle, I think, in maybe coming up with an alternate reason as to why the Stern-Gerlach experiment shows is detecting electrons going up and electrons going down, and it has nothing to do with up electrons and down electrons. It is my opinion. It's my opinion that the dipole moments as they pass between the two magnetic configurations, the north being up here and the south being up here, it's my opinion that they will always align correctly, as you would expect, that they would never by their own devices because they're flying through the air. They will never anti-align perfectly. It's almost impossible to do that. When I tried to take the small magnet and anti-align it to the big spherical magnet, it was almost impossible to do that. There's no way that when the atoms are flying through the air in the Stern-Gerlach experiment, there is no way that they are going to anti-align with this magnetic configuration. Okay, I don't really see how that's possible. It is makes more sense to me. Okay, it makes more sense to me that because they are moving at velocity, they are getting caught up into the orbitals. Okay, these are now actually orbitals. They are orbits. They get caught into orbit, much like a gravitational object would get caught into an orbit. Okay, so here I have something that looks like a gravitational field, a gravitational gradient, and I have an object here. And clearly, if I just placed an object here or here or here, it is going to fall into the gravitational body. But if I send this gravitational body through, if it is going at velocity of some sort, it is either going to just curve and fly away if it has enough speed, and if it doesn't have enough speed, it is going to get caught up into an orbit. Okay, it's going to get caught up into an orbit around this gravitational body. Okay, and so I see the same thing going on here. Okay, so here we have a small dipole moment in the vicinity of the large dipole moment. And let's say it's aligned like this as it's coming out of the device that shoots the silver atoms, that heats up silver atoms, and they're moving in this direction. Okay, so as, as it gets closer to the big magnet, it is going to start to align. Okay, as it goes exactly between, while it is going exactly between the two magnets, it is going to be exactly aligned. If it's going exactly between, it's going to be exactly aligned. But at some point, if it's even a tiny bit above the dielectric inertial plane, it is going to start to curve. Okay, it's going to start to curve. Maybe it gets caught up in this line. Now there's all lines in between. I'm only showing you the lines that depict the gradient, the 1 volt, 2 volt, 3 volt, whatever. But you can see, let's say there's a wall over here, so you can see if it gets caught up into this isopotential curve, it's going to, and it always has to be orthogonal to this curved line. Okay, so you can see that it is going to go in this direction and potentially hit a wall or hit a detector over here. But if it gets caught up into if it's a little bit below the inertial plane, then it's going to potentially get caught up into this isopotential, and it's going to curve along this isopotential like I showed you in the video, and potentially hit the detector right here. So it is less likely to happen here because there are, it is less likely to hit the wall over here, mostly due to the probabilistic, okay, so it's probabilistically less likely to hit the wall here than it is to hit the wall here. And so this sort of combines the language of the orbitals with the idea of an actual, potentially an actual orbit. These magnets actually following an orbit because they're going at a velocity and getting caught up into one of the orbitals, and inadvertently hitting a detector on the way. Okay, so looking at this problem from the perspective of the isopotentials rather than the magnetic field lines gives us a potentially a different interpretation of what is going on in the Stern-Gerlach experiment, in a potentially different explanation for why we see a clear separation, why we see targets here, we see electrons hitting this part of the target, but not in between. Okay, so that is the main point I wanted to make. This video has been a long time in the making because every time I go to make it, I get another idea or another way of explaining it. And so I think this is the best way of explaining it. I think connecting all these concepts together. Okay, the orbitals of the electron probability distributions in the atom, connecting that with the isopotentials of a magnetic field, and connecting that as well with the sound fields radiated by simple sources, bringing all these things together into maybe a communal concept, the property of self-similarity between these seemingly very different physics scenarios. I would like to try to bring them together into a common theme so that we can better understand what's going on with these experiments. Okay, so that's all I'm going to say for now, and I'm going to leave it at that, and hopefully you're having a good day, and well, I'll be back.